I'm gonna share my screen. Okay. This is going to be a bit of an interactive thing as well. Actually, interactive, nah. But the thing is, while this is going on, if there's any questions, ask right now because it's. I mean, if you go further down and if you have a question, it might be a bit difficult to explain because there's a lot of theory to cover today. So we'll try to. So the idea is we'll try to cover some parts of machine learning and some parts of different branches of machine learning, but overall thing would be focused towards deep learning because I think that's the topic today. So we can't jump right into deep learning, so we are going to cover some theory basics as well. If there's any questions, let me know. All right. So let's start with machine learning. What machine learning is, and what I let's actually start with AI because like everyone's now talking about AI these days. Um, AI is not a specific term. Like AI is not something that we can pinpoint. It's a broad term, umbrella term that has a lot of subdisciplines. So we have machine learning, we have expert systems, robotic process automation, semantic web. There's like hundred of different things inside AI. So usually, artificial intelligence involves some form of combining human intelligence and capabilities into a machine. So the general idea is we are trying to make a machine do something to behave like a human. It can be vision, it can be language processing, it can be data analytics, it can be pattern recognition. So there's a different like a lot of branches in the AI that's in it. So today what we are going to go into is machine learning, which is one specific subdiscipline in AI. So what machine learning is teaching a machine to do a task without explicitly telling how, by giving the input and expected outputs. So we all knows this first diagram, right? I think this is what you see in your, I don't know, whatever ITO, ITO, whatever the first IT whatever the first IT lesson you do. So a computer program is something that gets the input, does some work, and gives an output. That's the definition of a program. So in machine learning, what we are trying to do is we have this additional step called the training. So what it essentially does is we have a non output for a given set of inputs. We use that and send it through a process called training, so that the program is created by this training. So there is like a very high level generalization of the machine learning concept, but then again, in high level, that's what we are trying to do. We are not trying to create the program, we are trying to create a training program that's going to create the program behalf of us. But in the new program, if we give a new output, what we are getting is not the output, it's we are getting the predicted output. I'm saying this is as the predicted output is because it's very important to keep in mind that a lot of machine learning models are not absolute. Like the output you are getting won't be an absolute truth or absolute false. So it's very important to keep in mind that we'll get to this when we are going through when we are going further down the line as well. But things are not, machine learning outputs are not absolute. Those are always probabilistic. Those are always relative. All right, let's okay, so sorry. So to keep things to get through things fast, what I'm going to do is I'm going to give you a structured approach into machine learning. So machine learning is like 100-hour course, so I can't really give all of that today, but I'm trying to give you a structure. The structure you can then use to eventually learn about all the different disciplines maybe after this, but I'm going to give you the fundamental knowledge. So there's a lot of jargon, like there's a lot of, I mean, if you Google what are the types of machine learning, you are going to get a mixture of all of these. You're going to get supervised learning, regression, principal component analysis. There's like 100 different shits out there. So we'll see what exactly are the different types and how all of these different things fit together, so that you can like declutter this noise around it. So when we say machine learning, we say that there's going to be a, learning process. So there are four types of main learning processes in machine learning: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So we'll go through each of these different learning types. Maybe not semi-supervised learning. It's not. I mean, it's not that important. So first one, before we go to that, some notations, because when I'm explaining some things, these notations will come in handy. First one is, usually when we say X, it's usually the input, the sample, or the data point. So for whatever our black box that we call the machine learning program, whatever the input, we usually denote by an X. And for Y, we usually denote the outputs by Y. So if I say capital Y, those are the set of outputs for the given set of inputs. Capital X is a set of inputs. Simple X is an individual input. So so now when you say input, it can be one number, or it can be 10 numbers as well. Because let's say we are trying to predict someone's I don't know, you know someone's income by their age and their education. So in that scenario, if we are trying to predict that, there are two variables, two inputs per each sample. In each sample, we have their age, we have their what was the other one? We have their what was the other one? Age and what the education qualification. So two input, and we have one output, that's their average income. So those we actually call features. There's another word you have to sort of keep in mind. Features in that sample are the two things. I mean, in that particular example, we had two features per sample: the age and the education background. So just keep in mind of these notations. All right, supervised learning. Supervised learning means it's we are trying to teach the machine to do something by giving it some inputs and giving it some the corresponding outputs and asking the machine to learn this. So it's this mechanism where let's assume it's I'm trying to let's take Rusiru as a black box. I'm giving a set of inputs to Rusiru, saying that these are the different variables I'm giving you for this sample case. These are the numbers. For sample one, the numbers are 10 and 5, and the output is 15. So we don't know what exactly Rusri is going to do with that information. For now, Rusri knows that the inputs are 10, 5, the output is 15. And then again, I tell Rusri another example. You have 10 and 20, and the output is 30. So now by this time, Rusri is now getting a bit more understanding. Earlier, I'm just gonna use the board. If you can't see the board, you can tell me. So earlier, we have Rusri here. Earlier we had 10 and we had 5. So this is, I will call this X1. The X1 is in the set of capital X. Can you guys see this? So I'm going to say that the output is 50. Then I'm going to say this is 10 and 20 and the output is 30. So what I'm trying to do is I'm trying to give a series of numbers like this and telling Rusiru, figure out what's going on in here. So after I give 100 different samples, Rusiru might come and say that, all right, it seems like what you're doing is you are getting input 1, I will call it X1, and adding it to input 2 and calling it as Y. All right, so that's how we do supervised learning. I mean, this is like a simplification, but this is how we sort of do it in supervised learning. So in supervised learning, we have two key things, two categories inside supervised learning itself. That is classification and regression. It's easy. Classification is when you have like 5 different, you want to classify or categorize a set of given inputs, set of observations, and you want to assign something to it. If you have watched Silicon Valley, there's like this thing called hot dog, not hot dog. So you take a picture of any random object, and your model is trying to figure out whether it's a hot dog or not, or it's not a hot dog. So it's pretty. Yeah. So when you take a picture, so that's called classification because you have an input, you have observation, and you are classifying it as a hot dog or not hot dog. The other one is regression. Regression simply means you have a set of inputs, you have an observation, but you are trying to predict a value. So you are trying to say, give a definite value to it. So we call it a prediction. It can be, let's say, the rainfall. So we get different kind of features, the variables, and we are trying to predict the rainfall today. It's going to be 21 millimeters. So 100 centimeters, whatever that is. So those, this is the two categories inside supervised learning. So the difference here is in classification, you are trying to pinpoint to say that this belongs to this particular class, whereas in regression, you are trying to say that I'm going to give this much of probability, or I'm going to give this output to this particular task. So here, what this is going to be is regression, right? This is not going to be a classification because you are not classifying your output, but rather you are regressing your output based on the given inputs. So that's a supervised learning. Any questions? If you have questions, just ask away. You can ask while I eat. Mm. So let's get to unsupervised learning. So naturally, unsupervised learning is the okay, so that's natural. So unsupervised learning means unsupervised learning means you are only giving inputs to your learning model, and then you are asking your model to do something with it. You are not giving outputs. That's why it's called unsupervised. So you are giving inputs, and you can ask your model to do one of two things. One is cluster, one is associate. So cluster is, let's say mm, you have data points like people in the office. So let's say we get all the people in the office, and you get some characteristics of them, their age, what they like to do, things like that. So in using clustering, we tell the machine learning model, okay, divide this group into 5 clusters based on something. So we don't know what the machine is going to divide them based on, but we know that they would divide them into 5 groups in the end. So clustering is a way to identify samples that have some common property that we don't know. Finding the property would be the next step in usually in an analysis. So we have like 100 people. We have each person have some sort of like features. We call them, I mean, since we know the notation, we call it features. And the model will cluster them into like segments, and we would know that each segment would have something in common, but we don't know what the common feature. Sometimes we know beforehand what it is, but usually that's what happens. Another thing we can do is association. That is, we give a set of inputs, and then we tell them to we give a set of inputs of each person, and or are the features of each person, and we'll tell the machine identify dependencies or relationship between their features. So let's say each person in the office, we characterize each person in the office by 10 different features, then 10 different inputs. So we can tell the machine that, okay, maybe age and affinity to go out are related. For example, since Amal is old, he might not like to go go out and party like the rest of us. So this so we don't know that before putting it into unsupervised learning. But if we put what I'm saying is, if we put Amal's features into a model, it's likely that the model would say that there's an association between the age and inability to go out and party. That's not part of today's. Okay, and then there's one other thing that is semi-supervised learning. So semi-supervised learning is not widely used, or it's not like a principal classification, but it what essentially says it. You give some sort of small amount of labeled data. You do a bit of supervised learning and let the machine do the rest. So it's a combination of supervised and unsupervised learning. So you don't have to worry too much about it. But this this diagram here actually explains the two learning classes really well. You can see in unsupervised learning you have some dots, and what the machine does is classify these dots into clusters. So these dots are placed in that vector space. We call this a vector space. So we have two variables, x and let's say x and z. So in this space, you can see that those are like when you draw these circles inside this vector space, you can see that some circles are close together rather than the others. So that means some feature in them makes them more closer together than the others, and that's the feature we are trying to find out. That's the feature that makes them cluster together. Whereas in supervised learning, it's very clear we are trying to find this boundary. Yeah, we have two types of dots, the red dots and the green dots. What we are trying to find is this boundary, so that once this machine learning model knows this boundary, any new dot that's coming into this graph, we can put it into green side or the red side. Hope that's clear. All right, and then we come to reinforcement learning. So reinforcement learning takes an entire different approach into this learning mechanism. Rather than giving inputs and asking the model to create outputs, the reinforcement learning asks the machine to maximize or minimize some reward function. So like things like self-driving cars, autonomous agents, things that interact with the outer world mostly, but not only that. Things like that doesn't have a clear input to output, but is trying to do something so that maximizes another function, usually a reward, are examples for this. So these machines have a set of policies as input, like if it's a auto driving car, the policy would be if you kill passengers, that would be bad. So it's a it's a very bad. So that would be a negative reinforcement. But based on who you're killing as well. So if you're killing a terrorist, it would be considered as a good. So the so the you'll see the reward function and the policies itself is a bit difficult to define. But once you define it, you ask the machine to just act on their own. The acts you can define as well, but act on their own such that the cumulative reward is maximized or minimized depending on the use case. All right, that's on the different types of learning. So is everyone clear on how we classify the key learning types, and how the each classification has its own different categories, inner categories. So this is important to know that there are different hierarchies when you are talking about machine learning. When you are navigating through tutorials and everything, sometimes people mix these together. Sometimes you would see that supervised learning and I don't know, top three machine learning methods, supervised learning, clustering, and association, or something like that. So those are not the same. You have to figure out, you have to denoise, declutter the different concepts into different baskets, because if not, you are like, like just going in the blind. All right. Now we come to machine learning models. So earlier we talked about machine learning classification. Now we come to models. So a machine learning model is a way of implementing a machine learning technique. So any the supervised learning method, the clustering, unsupervised learning method, clustering or classification or association, things like that. How we actually implement, what's the algorithm of implementing this, comes under the machine learning model. Like a lot of people think machine learning models are like black magic, you do some things, there's some random code, there's some random binary code that does thing. It is not. It's actually all the machine learning models are just a bunch of statistical or mathematical approximations. So each machine learning model, you can always define a mathematical equation or a probabilistic equation to explain the outputs given a set of inputs. So for an example, if you are given a set of inputs, and if you are given a paper and asked to calculate probabilistic outputs for a given machine learning model, like you are given a pen and paper and you are asked to create a artificial neural network and do calculations and everything by hand, you can do it, because it's not some binary sort of a computer thing that's there. It's a very mathematical thing. We are simply using computers because they are more efficient in calculating those. Theoretically we can do any of the machine learning things on paper as well, which makes it like paper learning or something, but you get the point. So machines are more efficient in doing that. That's why we are using machines. So The widely used machine learning models are the regression models, decision trees. So I'm not going to explain each of these, but I highly recommend that you go and learn about these. So regression is, I think, linear regression. Pretty much all of you should know if you have come from a computer science or a IT background. Linear regression, or maybe even maths, if you have done maths or something. But linear regression is simply, like, you try to. We'll get to linear regression later. And decision trees is like, is exactly as it sounds. Decision tree is a decision tree is a tree where at each point of the tree you are trying to take a decision. So we are trying to, let's say, classify, okay, let's say we are trying to classify hot dogs or not hot dogs. So we may have different features. We may have what's the bun used, what's the sausage used, things like that. So how the decision tree works is, initially it looks at some, takes one of these questions: what's the length of the bun? If the length of the bun is less than three more than 3 feet, it's unlikely it's a hot dog. If it's less than 3 inches, also it's unlikely it's a hot dog. So like that, you can, it will create a populated tree. So the machine learning part is that we are not populating this tree by hand, because we can do it by hand as well, but that's beyond the point. Machine learning means the learning model is going to populate this tree. So that's decision tree. Support vector machines is something I don't think I can explain within the hour. It has a bit more. It has a vector space arithmetics and things like that. But if you just read an article, you can figure it out. Naive Bayes again is a probabilistic model. So I told earlier that these models break down into, I think, 3 categories. I would say 2 categories. One are statistical models, the others are probabilistic models. Linear regression, decision trees, vector machines are statistical models because they are based on statistical principles. Naive Bayes, on the other hand, is a probabilistic model because it is based on the theory of probability. Like, yeah, I don't think I'm going to explain that either, because so each of these has a lot of base theory. But for the context, I don't think most of you would actually need this theory to take a use of these models, because most of these models come as utility in a lot of libraries. But you should always know what this model does in a very high level. In your head, you have to know that, all right, this is how this model comes into predictions. Because if you don't know that, you are just simply, running models over data and trying to figure out why it's not working. Each data problem should be mapped to a unique model, and each model has its own strengths and weaknesses. So that's something you have to know. Knowing the exact math around it, I don't think that's a necessity. And then you have principal component analysis, and then comes the star of today, that's artificial neural network. So I think we are going to move into artificial neural networks from here. Is there any questions up to now? Anything that's not clear? Anything that is clear? All good? Hold up. All right. So before coming to ANNs, or artificial neural networks, let's start with linear regression. So we all know linear regression, right? What we are trying to do, we are trying to find out the relation between x and y. So let's take a very simple example. We are given so this is your Cartesian plane. This is your x-axis. This is your y-axis, and you are given a set of data points. I assume you can see this. You are given a set of data points. Let's say you have a data point here, you have a data point here. Let's make it simple. You have a data point here, 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 here. So it's like as easy as it gets. You given these data points, linear regression. What linear regression is that we know if this is our plane and this is our data points, we can assume that the relationship between x and y has a nature that's something like this. This is, I mean, സാധാരണ ഗണ്ഡഗോളം because we have only one variable, so it has to be mx plus c. There cannot be any other forms, taking it in a very generic manner. So linear regression, what you're trying to find out is what is m and what is c. So how to do this? One way is like we take this y value. So let's say um, this is 5, and then we take this x value. Let's say this is 2. So it's 2m plus c. Again, let's say we take this one. If it is like 10, and this is 4 plus c. So you have two equations, you have two unknowns. You resolve this, you will be able to find the two variables. This would come something like this. I mean, yeah. So this is more or less, we can assume that line to be something like that, and we can give it a name. Y equals, let's say, 5x plus 10 or something like that. So that's linear regression. So this actually, I mean, we can do this on hand, right? We don't need a machine to sort of do this. I mean, when it comes, this is like integers, but when it comes to floats and all, it's going to be a bit difficult because now we have to, have a lot of precision points. But then again, this is not that difficult. This is not nothing voodoo magic or anything. Then things becomes a bit tough. Let's say we have two variables, two features. We talked about earlier when you have your age and your education status. Now we have two variables and one output. So what happens now? So now our initial equation of y equals mx plus c does not hold because we have two x's. It would be y equal m1 x1 plus m2 x2 plus c. So now we have to find three things. We have to find m1, we have to find m2, we have to find c. And visualizing things are a bit difficult as well because earlier it was on a 2D plane. Now it's like in a 3D plane. We have to, like, we can't really visualize things, try to draw it out and, hack our way through it. So that's a, that's a bit of a problem, but still nothing too concerning. So if we, everyone of you should be, most of you would be able to sort of create a sample, very simple Python program or something like that, that would iterate and find an answer given enough data points. So given enough data points, that's also important to know. And now we're gonna complicate this a bit more with polynomial regression. So what happens when we actually don't know whether the relationship between the output variable and the input variable is not, like in like what do you call it, linear. So your x variable might affect two times rather than your x1 variable might affect two times rather than your x3 variable. So this is when things become really difficult because you wouldn't know. Now we have, if we get the same equation, now we will have a and a b above here as well. So and now we have 1 2 3 4 5 different things, and computing these polynomials takes a lot of processing time with respect to computing the linears, because polynomials add up, like it needs more computing power. If this, I mean, in the long run, you can see how this is not going to scale if it comes to a new problem. If it comes to a new set of data points, now we have to again go all this process. We have to figure out whether it's a polynomial, whether it's a linear, multivariative. So there's going to be a lot of issues coming up. So I can take this a step more forward and make it more complicated. What if there are relationships like something like this, x1 into x2? So what if the y somehow depends on x1 and x2 by having an independent, I mean, having a multiplication among themselves? So something like this, there's no way we can solve with just regression. So this is sort of is like the problem point we are at. Like we can have these inputs and outputs. The mapping function can have any of these forms. We don't know the forms. Even if we knew what form it is, we would have hundreds of different variables to figure out. sometimes we might actually not have enough data points to figure out this either. So we need something that scales, that works better. So that gives us that. So the solution we are trying to get to is called the neural networks. So neural networks. So neuron is actually what you have in your head, right? I'm pretty sure everyone has it. So we gotta stop bashing on. So neurons are the basic elements in your brain. Mm, so the neural networks are modeled using how the neurons are formed in the brain itself. So we call it a perceptron when we come to our mathematical implementation. We call it a perceptron. You are looking here in the slide. You are looking at a perceptron. So a perceptron is essentially a mathematical function that takes in a weighted summation of inputs and take in a bias and or gives an output. So we can define it as fx equals w1 x1 w2 x2 wm xm plus b. So w1 x1 means we take x1 input but we add a w1 weight to it, so it can be it's something like m1 x1. That's when it's similar to m1 x1. And we can generalize this and we can write this as fx equal w dot x plus b. If you have done a vector arithmetic, you know w dot x means w vector multiplied by the x vector plus b the constant vector. So what this is how we define a perceptron mathematically, and you can see this actually is now a bit similar to what we had here in our multivariate. Someone's getting cold. Hold up. So this is now getting similar to what we have in the multivariate regression. And one change here, apart from multivariate regression, is that at the end of our perceptron, there's something called an activation function, which is called G. You can. I'm not again going to go through a lot of depth into activation functions. There are different ones. There's like sigmoid. There's like logistic, sigmoid, log, inverse log. So there are different activation functions. What the activation function does is that when you get an output from your perceptron, it tries to manipulate it so that it gets to a different shape that we need. For an example, the activation function you are seeing here right now is the sigmoid, I think. What the sigmoid does is if your y value is above, let's say 5, it takes it as 1. If it is less than 5, it takes as 0. So it's like, like it converts your discrete rather continuous, sorry, take your continuous output and map it into a very a push down output so that you can use it in a different place. So this is useful when you are trying to get these perceptrons to work together. So we'll see that in the next slide. All right, so we had one perceptron here. What we are going to going to do next is we're gonna get these perceptrons and then combine it to create a hidden layer. So we are going to get your perceptrons one by one. Let's say we have 3 perceptrons here, and then we have one here, and this essentially creates our neural network. So this is one of the simplest neural networks you can have. You can actually have with just 2 neurons or 1 neuron here as well, but I'm just So this we call the hidden layer, and then we have our inputs. Let's say we have 5 input features. So x1, x2, x3, x4, x5. So each of these inputs are connected to each of these perceptrons. So each connection here would have its own weight. So this one would have weight 5.1, weight 5.2, weight 1.1. It's going to have its own individual weights. And each of these perceptrons also going to have its own bias. So that's going to be like, I'm going to say B1, B1, B2, B3. So each one has its own, I would say, F1x, F2x, F3x. And now here's the interesting thing that happens. Now the output of these becomes the input to this the last layer, the last perceptron in your neural network. So all of these then connects here, and these act as the inputs to this perceptron. So if we get y, this one would be there would be some weight, let's say W1, W2, W3. It's going to be W1 times F1x plus W2 times F2x plus W3 times F3x, and it would, and plus B4. This would have a bias B4. This gives y. So the y is our output, and these are our input. So y is our so this is x. This is essentially the function we have now created by using these perceptrons. Now you can see that if we take f1x, I'm just gonna zoom into f1x here just for that. F1x again is a function of w into w, let's say 1 into x1 plus w12 into x2, like that. So in this f1x, you already have a accumulation of your inputs inside, which means when you expand it, you get terms like w1 x1 squared, or w1 x1 x2, w1 x1 x3, or w1 the x2 squared. So you are getting all the possible polynomial and polynomial terms inside the output of y as well. So this is important because now you can see if you increase the number of perceptrons here, you increase the number of different combinations you are including in your y value, which means your neural network increases its ability to think more in a very holistic manner, which means it's like giving more brain capacity to your neuron. If you give more brain capacity, it can handle more complex functions. If you get less brain capacity, it can handle only less brain functions. So on the other hand, one something you would also need to figure out is that if your function is really simple, and if you give, like, 100,000 neurons for in brain capacity or neural network, it is going to be just wasted, because most of these w values, more of bias values, going to be zero, because they do not affect directly to the output. So one decision you have to take when designing your neural networks is that depending on how complex your problem is, you have to select how many neurons, how many brain capacity you have to give to your neuron. So since we have only one hidden layer, this is called a shallow neural network. That is the simplest form of a multi-layer perceptron. So if you want to the next thing what we can do is, now this is just one layer. Let's say we make more layers of this. Let's say we have 2 layers of this. You can now see, if you just do the math in your head, you can see that we are now getting more polynomial terms in that. So in this one, you can only have x1 squared and x1 x2 terms. If you have another layer in front, you now can take x1 cube, x1 x2 x3 kind of outputs as well. So you can keep increasing the layers in your network, and the ability for your networks to assume your function becomes better and better if the function is much more difficult, much more complex. So this we called a deep neural network. So deep neural network is a neural network that has more than one hidden layer, and there can be like hundreds of layers in the middle, and it can accommodate a lot of complexity than your average regression model or your average perceptron. So any questions at this point about like perceptrons, neural networks, how the math works, anything? So to give a bit of an idea how the computers work with this is, like, in the computers, all of these boils down to vector arithmetic. Each computation becomes a vector computation, or your input is a vector. Everyone knows a vector, right? Vector is simply a set of integers, so set of numbers that's defined, that puts maps a set of numbers in some sort of a dimensionality. So each of your inputs, your or your weights and biases, all of these becomes vectors. And when you convert them to vectors, all of these vector arithmetic simplifies into matrix simplifications. So computers, or rather GPUs, are really good at matrix simplifications because they are good at parallel processing. So when they are good at parallel processing, that's why deep learning and everything use a lot of GPUs like CUDA and all of this, because your GPUs are really good at parallel processing, and this is the perfect opportunity for them to integrate parallel processing into it. So that's why we use a lot of GPUs when training neural networks. All right. So neural network learning. Now, just because we have this network and we put some inputs and outputs, doesn't mean that the network would really know anything, right? So let's say we design our neural network with 100,000 neurons. We have like a set of inputs, we have some set of outputs. We now want to figure out what the function is that maps these inputs into output. So this process is called training, or rather training your network. So what training does is, we are trying to approximate as much as possible these weights and biases inside our neural network, so that the output comes really close to the predicted output, rather comes really close to the actual output. So when I say predicted output, this value y we are getting here is actually, it's not y, it's y hat. It's like put a hat onto it. We call y hat a predicted value because it's something we are just computing from our network based on the inputs. It's not the actual y value. Actual y value we already know, because this is a supervised learning process. We already know for these x values, this should be the y value. We call that the y value, the target value, whereas we call the prediction we get from the network y hat, the predicted value. So naturally, what we are trying to do is, we are trying to minimize this gap between y and y hat. So let's say y and y hat is the same, which means we have won. Our network can accurately predict the output given some input, or our network has overfitted, which is something we'll get to in a moment. But in a high level, what we are trying to do is, we are trying to remove this gap. We are trying to minimize this gap between what we think is the output of a given set of inputs versus what actually is the output of a given set of inputs. So the process of training is initializing your network with random weights and biases. Let's say you have 100 neurons in your network, and you initialize with random values for your weights and biases, and then you calculate fx for a given x, so that we can get the y hat value. So we find this y hat value given from the data points you have. Let's say you have 100,000 data points, you have 100,000 examples for each iteration. So when, let's say, when we send out all 100,000 to the network, you get 100,000 y hat values. We get 100,000 y hat values. We calculate hotspot. Oh, yep. Where lost generally preserving. Okay, I assume it lost a lot. So the average of the differences of y hat and y values is what we call the cost. What you're trying to do is to minimize this cost, because that's the inverse of your cost is your accuracy. So your accuracy is, if I say it without losing generally, your cost, your accuracy is 100 minus your cost, maybe the cost percentage or something. But you get the idea. You really minimize your costs, you improve your accuracy. So how to actually do it is that's actually where the tech comes in. Now all of this you can still do it on a paper. You can just like we have done it on paper for exams. But what you want to do is now to have a algorithm that can actually do this part, which we call back propagation. That is, you given your y hat value and your cost, and your y value, we now want to adjust your weights and biases so that your y hat value gets closer and closer to y. So this is called backpropagation, and this is the process of it is called the optimization algorithm. The most commonly used optimization algorithm is the gradient descent. So gradient descent is a bit of a complex thing to explain, but visually, I think you will get an idea. You can see that we have two weights, WA and WB, and we have our cost. This is y minus y hat. What we are trying to do is to find WA and WB in a way that we minimize the cost. So you see, we start with a very high cost here, and then it's like we are rolling three balls in some, like a random plane that's drawn based on what we get as for WA, WB, and cost. And we are trying to minimize the find WA and WB such that we are minimizing the cost.
So this animation is for one y hat value, right?
This is
Is it for
is
the
it
entire thing?
entire thing.
Okay.
Because now when you get WA and WB, there can be like 100,000 samples. Your cost is your average out of that 100,000 samples.
Yeah, so let's I mean you are going one by one, right? Or
Mm.
you are going by one example by one, right?
In each epoch, you go with all your samples, or rather set of your samples. So let's say you have 100,000 samples. In first epoch, maybe you train with only 50 of it. So those are different training techniques.
Okay, so let's say we take one epoch.
Yeah.
And then inside that we take y hat one.
Just one sample.
Yeah.
Okay.
And then what happens then? I mean, let's fix the window to one value.
Okay.
And then what could be the algorithm doing?
So what the algorithm do is now at this point we know y hat, and we know y, and then we calculate the cost. Cost is y hat minus y divided by 1, that is still y hat minus y, and we map it on our plane of WA, WB, and cost. So we know the point. And in the next, now we don't have enough information. What the algorithm does is it backpropagates. I haven't visualized how the backpropagation works, but essentially it tells W and WB that this is the value we got. You have to change your value so I can be lower.
Okay, do we do that in that cycle, or do we do like, let's say, one epoch and then
In the next epoch we change values. So
for this one we only record the value.
Record the value.
Okay.
So then we change our W and WB in epoch 2. So epochs are actually iterations. In epoch 2, we change our W and WB values and see whether the cost increased or cost decreased.
Okay.
Sometimes the cost can increase as well. Then we know, okay, we took the wrong decision. We need to now change W and WB again and see whether how we can reduce the cost. So gradient descent is created in a way that this is sort of like finding the shortest path to the minimum value. And sometimes you may not go, the cost likely does not go to zero, because if it goes to zero, we call it overfitting, because usually in a practical scenario it can't go to zero. It will plateau after some time. Gradient descent helps to find this plateau after a while.
So when we are jumping between epochs, what they are doing is a local search and find the steepest
Yes.
from that point, and then go towards that and see.
Yeah, that's how the gradient descent works. Is that clear, everyone? No, any questions? Okay. So then, with all of these in mind, you can actually forget all of these. No, don't forget, but you can keep that in mind, but you can work without knowing this. But the key thing is designing and training neural networks. So that's what you're interested in. Like, that's what you want to do, or the outcome of this. So designing your neural network is not something you can learn logically. There's no logical way to say, yeah, okay, for this problem I'm going to have 2 layers with 5 neurons each. There's no logical process that tells you this. There are rules of thumbs. If the input features are 100, maybe you need 10 neurons. There are like different rule of thumbs, but none of this really gives you a logical way to design your network. So these are called hyperparameters in a neural network. So these hyperparameters, like how many hidden layers, how many epochs to run, how many neurons in each layer, what's the cost function or the loss function to use, what are the activation function to use. it is like more of a trial and error thing when it comes to research. But the good thing is people who are actually wasting their time doing this research luckily publish their research, and they create these baseline models, baseline architectures, so that when we want to solve a problem, we don't have to start from scratch. We don't have to start from one neuron, one layer, and keep increasing or something. We just get one of these existing base architectures and then trying to optimize it to our problem. So one example is convolutional neural networks. CNNs are the most widely used networks used for computer vision tasks like object recognition, diffusion models. All of these. This is like the basis model, basics architecture. So if you are trying to do image classification today, you are not going to go and try to figure it out using your own neural network. You are going to go and find a CNN that fits your use case, and then try to see what other researchers have done on it. And then probably, so if you're trying to do object recognition today, you don't need any of this. You just get YOLO model and use YOLO to do it. But what I'm saying is, if you are trying to do R&D, do not train start from the lowest level, because there are proven architectures that you can use. But other than that, if it's a really entirely new problem you are trying to solve, there's no way that you can imagine that this is a neural network that's going to be perfect fit. It's a trial and error. It's called hyperparameter training, and you have to go through it. So what's the so deep learning essentially is designing, training, and improving artificial neural networks with more than one hidden layer to teach machines to unravel complex patterns in data. So what we are actually doing is unraveling a pattern, right? We are trying to see that we have some observations, we have some inputs, and we have some outputs. What we are trying to do is, we can't see how these outputs and inputs are related. We can't see it as a human. So we are asking the machine to go and find out what's the pattern between these inputs and outputs. If it's like really random, it's like random inputs and random outputs, you won't find a solution. So that's why your machine learning model is only as good as your data. If your data is shit, your model is also shit. It can't do nothing if your data is shit. So the key learnings of this is that deep learning is not like some voodoo magic, or something that's very highly technical or something like that. Deep learning in its basis is highly mathematical. So if you are hoping to go deep into the theoretical side of it, you need to have a good understanding in vector arithmetic, probability, statistics, and matrices. But if you don't want to go deeper, but you just want to use deep learning for applications, you don't need to really have any of that. Deep neural networks is just a more complex version of an artificial neural network. There's nothing more to it. um, Basis of deep neural networks is approximation of mathematical equations. That's what we saw here. So for this approximation, we use optimization techniques. That is what the gradient descent is. So there's no logic in designing or executing deep learning. It's actually, one of our lecturers said that it's half theory, half knowledge, half art. Because you, after a while, if you are a data science researcher, after a while you get that sort of experience in your head that like, okay, for this I'm going to apply a structured support vector machine. For this I'm going to do a reinforcement learning, random forest, something like that. There are rules of thumbs you can use when you want to use, but the most successful way is that when you have a problem, go figure out if there is a base architecture that someone has already done, because there is always something someone has done as a base architecture. um, what next? So this today, what we are trying to do is to just give you the very bare metal, the bare fundamentals into machine learning, and then to navigate you to neural networks, and from then to deep learning and deep neural networks. So this is in no way a comprehensive guide for machine learning or any of it, but the idea is that this would act as a sort of a skeleton, sort of a guiding mechanism, so that when you're actually going to go in depth to learn each of these subtopics, you are not overwhelmed, because it's a huge broad area. There's like a lot of developments. Machine learning is not a recently new thing as well. Machine learning fundamental theories were there since 1960s or something. The earliest papers were from 1960s. So if you are going deep into these things, don't be overwhelmed. Just know your basics, know what each of these different things means. So I would highly suggest that you go and study in these concepts, especially about underfitting and overfitting of models, about the ROC curve, the bias and variance. These three are fundamental and necessary if you are trying to train your own model. So if you don't know about underfitting, the different dangers and how to measure you whether you have underfit or overfit a model, you're going to end up again with a shit model. That's just, the model is just stupid, you can't use it. So learn about these first before going into training. And there are like three tour data science articles I have linked. Those are really good articles for you to get an understanding about individual like random rainforest decision trees and things. And maybe you want to look at probabilistic models as well, which is naive bias. The two key theories in probabilistic models are naive bias and hidden Markov models. So probabilistic models, if you want to get into generative AI, trying to figure out how generative AI works, probabilistic models will come in handy. I don't know whether in another session we want to do. I mean, we are going to do a generative AI in the next session, in one of the next sessions, so that we want you guys to get an you guys get to get familiar with generative models like diffusion generative models and diffusion models, mainly like the two hype things here, LLMs and the diffusion models. But I don't think we can actually do the theory around this. Maybe we'll, when it comes to diffusion models, we'll get Tejan to do some theoretical thing into it. But theory wise, those have a lot of background to cover, so it's not something we can do it in an hourly session. But try to learn a lot by yourself. When it comes to math, try to simplify and understand. If you're not familiar with mathematical notation, it might look a bit weird to you at first, but it's just math. I mean, math is math. There's nothing unmathematical about about that. So if you just look at it long enough, one of these times, you'll you will get to the meaning of it, or you'll go crazy. Either way, it's a win. So um, that's about it. Any questions? Which is it? All right, guys. I think that's about it. If there's any questions, put it in Slack. Is there anyone outside of Avanture here? No. If there's anyone outside of Avanture, just ping one of us directly, so we might be able to help with it. Okay, that's about it. And thanks everyone, and we'll see you with the next tech session, which should be a hands-on one. Probably, I don't know, maybe LLMs, maybe something else. Anything you want to say, Achala? Actually, we'll be doing the LLM. Yeah. Yeah. All right. See you guys. Bye.